All right, let's jump right in. We're doing a deep dive today into reinforcement learning,
RL, yeah.
RL. And this research paper, it really lays it all out there.
It really
The
is.
foundation of this whole field that's just, I mean, it feels like every day there's something new happening with it.
It is. It's absolutely exploding right now and having a huge impact on, all sorts of things.
You don't even realize it, right?
Yeah.
Like when a self-driving car
Yeah.
is navigating, a busy street or,
Or even.
oh, those recommendations you get on like Netflix or
Yeah, yeah.
Spotify. I mean,
That's all powered by RL.
it's kind of spooky how accurate they are, to be honest.
It is.
But that's the magic of RL, right? Like, it's almost like you're teaching a computer to learn from its mistakes,
Yeah, you can think of it like trial and error, just like we learn.
like we do in real life.
Exactly. Yeah. Imagine a robot trying to figure out a maze.
Right.
Every time it makes a decision, every turn it takes.
Uh-huh.
If it gets closer to the exit, it gets a reward. If it hits a dead end, it's
Yeah.
like, nope, penalty.
Oh, so it's like positive and negative reinforcement.
Yeah, exactly. And over time, it starts to learn, okay, which actions
Which ones work?
lead to the good stuff, to the
So
rewards.
you get out of the maze.
Yeah, and develops a strategy. And then it can, escape that maze like a champ.
So it's all about learning from experience.
Yeah.
And then changing how it interacts with the environment.
Exactly.
Based on what it's learning.
And that's what makes it so powerful, because it can adapt to problems that, are constantly changing.
Okay. Yeah, that makes sense. Because the real world doesn't stay still.
Right. And each decision affects the next one. So it's not just about making a single choice. It's like developing a whole strategy.
Okay, I'm starting to get it, I think.
Yeah.
But this paper, it uses some pretty technical terms.
Oh, yeah.
So what are like, I don't know, just a couple of the key concepts
Sure.
that anyone who really wants to dive into RL needs to
Yeah. It needs to get their head around.
really grasp? Yeah.
Okay. So one of the big ones is called Markov Decision Processes, or MDPs for short.
Okay, that sounds complicated already.
It sounds scary, but it's just a framework. Think of it as a way to break down any RL problem. You've got an agent, like our robot in the maze, and it's taking actions in an environment. And that environment has different states.
Okay, so like each position in the maze is a state.
Yes, exactly. And the robot's movements, those are the actions, and they cause it to transition between those states.
Okay, so the robot moves.
Yep.
Changes the state. Got it.
And as it interacts with the environment, it learns, how good or bad each state or each action is.
Okay, how do you determine that though? Like what makes a state or an action good or bad?
Well, that's where value functions come in. Think of it like a scorecard for the robot.
Okay.
It tells it how likely that action is to lead to, those tasty rewards.
So it's almost like, I don't know, like a map that highlights the best paths to take through the maze.
Yeah, that's a good way to visualize it. And then, based on these value functions, the robot develops a policy. And the policy is basically like, it's a set of rules.
Like a strategy guide.
Exactly. That tells it what action to take when it's in each state.
Okay, so the value functions tell it which states and actions are good.
Yep.
And then the policy is like, okay, now that you know that,
Now do this. Yeah.
here's how to actually like get to those good states.
Exactly.
Oh, got it.
And then there's this term that you'll see a lot, which is exploration versus exploitation.
Yeah, I was going to ask about that actually.
Well, it's like, okay, you've learned some things, but do you stick with what you know works?
Play it safe.
Or do you try new things,
Yeah.
just in case there's something even better out there?
So it's like, I'm trying to think of a good analogy. It's like choosing between ordering your favorite dish at a restaurant
Yeah.
or trying something new on the menu.
Exactly.
You know what I mean?
Like, do you play it safe or do you risk it
Risk it.
for a potentially tastier experience?
Okay, so in our maze example, the robot needs to balance between relying on its current knowledge and, like you said, taking risks to find potentially better paths.
Yeah, it's a delicate dance,
It's a delicate dance like everything in life.
but it's crucial for any RL agent to really learn effectively.
Yeah.
It has to find that balance.
Now, this paper gets into some different techniques that RL agents use to learn, right? And one of the big distinctions it makes is between model-free
Yeah.
versus model-based learning. Can you sort of like unpack those for us a little bit?
Yeah, sure. So in model-free learning, the agent is learning directly from experience. It's not trying to create a map.
It's just going for it.
Yeah, it's just like jumping in and doing it.
Like learning to ride a bike by.
Yeah, exactly. Just hopping on and going.
Just going for it and falling a few times, probably.
You'll probably fall a few times, but eventually you figure out, right? Just through trial and error.
Okay, so it's all about learning by doing.
Yeah, without overthinking it, without trying to, you know, model the entire world
Now,
first.
model-based learning, that's the opposite.
Yeah, so model-based is more like, okay, let's try to figure out how this environment works.
Like figure out the physics of riding the bike.
Exactly. Yeah, like understanding the rules before you even get on.
So it's more like studying for a test.
Yeah, it's a more analytical approach. Yeah.
Okay, so those are the two big categories.
Two big categories, yeah.
Are there like specific techniques that fall under?
Oh, yeah, there are tons of different algorithms.
The paper mentions, like Q learning
Yeah.
and model predictive control.
Yeah, those are great examples.
Can you give us a quick overview of those?
Sure. So Q learning, that's a really popular one.
Yeah, I've heard of that.
It's a model-free algorithm. Remember those recommendations we were talking about earlier?
Like on Netflix and Spotify?
Yeah, Q learning is behind a lot of those.
Really?
Yeah, it helps the agent figure out, okay, which actions lead to the most clicks, the most engagement.
So it's like a personal shopper for AI.
Yeah, that's a good way to put it.
Okay. And what about model predictive control?
So MPC, that's more of a model-based approach. It's all about planning.
Okay.
And it's used in things like robotics and self-driving cars where you need to predict what's going to happen.
Got it.
Think about a self-driving car trying to navigate traffic. It needs to predict what other cars are going to do.
And make decisions really fast.
Super fast, in real time, to avoid collisions, stay on course.
That's MPC.
That's MPC in action.
Okay, so that's a really good example of how, these RL techniques are actually applied
Yeah, it's not just theory.
out there in the real world.
Yeah,
Which is, I don't know, I find it fascinating and a little terrifying.
a little bit of both.
But this paper, it doesn't shy away from the challenges of RL either, right?
Right, yeah.
It talks about something called the deadly triad of instability
Yeah, the deadly triad.
in RL training.
Yeah, it sounds very dramatic.
It does sound dramatic, but what's that all about?
So, as impressive as RL can be, it's not always easy to train these agents. They can be a little unstable.
So the deadly triad, it's basically three factors that can really mess things up during training.
Exactly. Yeah, they can interact in ways that make the learning process, unpredictable, unstable. It's like trying to bake a cake, but the recipe keeps changing, the oven temperature is fluctuating, and you're trying to learn from someone else's baking disasters all at the same time.
That sounds like a recipe for disaster.
It can be.
Not a very good cake.
No, not at all. But luckily, researchers have come up with some really clever workarounds like target networks, experience replay, double Q learning.
Okay, and those help kind of
They help stabilize things.
stabilize the learning process.
Yeah.
So you actually get a cake at the end of the day.
You get a cake, and it's hopefully delicious.
Delicious and not burnt.
And not burnt, exactly. We can get into those a little bit more later if you'd like.
I think we should, because I'm very curious about those. But first, the paper also mentions a couple of other concepts that, I don't know, just sound really intriguing.
Yeah.
Things like distributional RL and intrinsic motivation.
Ooh. Yeah.
What are those all about?
Those are some areas where things are getting really interesting, I think. So distributional RL, it's about looking at the whole picture.
Okay.
The whole range of possible outcomes, not just the average reward.
Okay.
It's like a financial advisor who's considering your whole portfolio.
The whole portfolio,
Not just your average return. Because, sometimes you have those big wins and sometimes
big losses.
So it's about being prepared for anything.
I like that idea, because the world's unpredictable.
It is.
And what about intrinsic motivation? It sounds like we're giving AI a sense of curiosity.
Yeah, that's a good way to put it.
Which is a little mind-blowing, if you think about it.
It is. It's like, can we make AI curious?
Yeah.
So it's about giving agents a drive to explore and learn just for the sake of learning.
Not because they're going to get a reward.
Not for some external reward, yeah.
Okay, like a child playing, right?
Yeah, exactly. Like a child playing with blocks. They're not doing it for a prize.
Yeah.
They're doing it because they're fascinated by how the blocks fit together, what they can create.
Okay, that's a great analogy.
And there's research that suggests that actually makes RL agents learn better, more efficiently.
Wow, that's so interesting. Okay, so we've got these really cool concepts.
Yeah.
Distributional RL.
Yeah.
Intrinsic motivation.
Yeah.
And then the paper also kind of hints at where RL is headed.
Oh, yeah.
Right, like what's next? It mentions hierarchical RL and offline RL.
Two big areas. Yep.
Can you a sneak peek of what those are all about?
Sure. So hierarchical RL, it's all about breaking down big, complex tasks into smaller, more manageable chunks.
Like subtasks?
Like subtasks, yeah. Think about building a house. You wouldn't try to do it all at once.
That would be chaos.
Well, you'd break it down into stages, right? Laying the foundation, framing the walls, installing the roof.
So hierarchical RL does the same thing for AI.
Yeah, it makes it possible to tackle much more complex problems.
Okay, that's really cool.
And then there's offline RL,
Which
is all about learning from data that's already been collected without actually interacting with the environment.
So like learning from the past.
Yeah, learning from the past.
Okay.
Imagine training a self-driving car, but just using data from past driving trips.
Not letting it actually drive.
Not letting it drive itself.
That sounds really hard.
It is. It's really challenging, but it's also a really important area of research because in a lot of real-world applications, you can't just let an AI agent loose.
You can't just let it learn.
No, it's too risky.
Like in healthcare.
Exactly, like healthcare or finance. You don't want an AI system experimenting on real patients.
Right, right.
So offline RL offers a way to leverage existing data without putting people or systems at risk.
Okay, so you've got hierarchical RL tackling complex problems, and then you've got offline RL learning from past experiences.
That's a good way to summarize it, yeah.
That's amazing. I'm like, my mind is already blown, and we're just getting started.
It's just the tip of the iceberg, really.
I know, but I am really eager to dive into those real-world examples.
Oh, yeah.
Like AlphaGo.
Yeah.
And Dreamer and all that good stuff.
Let's do it.
Yeah.
I think those are great illustrations of how RL is being used to really push the boundaries of AI. Okay, so AlphaGo, I mean, this system really captured the public's imagination.
It did.
A few years ago when it beat a world champion Go player.
Yeah, that was a big deal.
Which is incredible because if Go, it's an ancient game.
Yeah, and super complex.
Super complex. I mean, more possible moves than there are atoms in the universe.
Atoms in the universe. Okay, so how did AlphaGo even begin to wrap its, digital brain around that?
So it's a combination, really, of deep learning and reinforcement learning. So researchers trained AlphaGo on a huge, massive data set of human Go games.
Like feeding it all the knowledge.
Yeah, all the best moves, the strategies from the top players.
So it's kind of like, I don't know, like if you're trying to get good at a sport.
Yeah.
You'd watch videos of the pros.
Yeah, exactly. Study their techniques.
But AlphaGo didn't just stop there.
No, it didn't just watch. It actually played millions of games against itself.
So it was learning by doing?
Yeah, using RL to really fine-tune those skills and develop its own unique strategies.
So it's almost like it bootstrapped itself into super intelligence by playing against itself.
Yeah, and it worked.
Clearly it worked.
It beat a world champion.
And not only that, it was coming up with these moves that had never been seen before.
Like brand new innovative moves that even Go experts are just scratching their heads like, where did that come from?
So this wasn't just copying what it had seen.
No.
It was actually creating.
Yeah.
That's both fascinating and a little unnerving.
It is, it raises questions about the potential of AI, right? What can it achieve if it can?
Yeah, if it can innovate.
And this type of self-play, it's become really important in developing other powerful RL agents like AlphaZero and MuZero.
Now, speaking of pushing boundaries, you mentioned Dreamer earlier.
Dreamer.
This paper describes it as a model-based RL algorithm. And it can learn to do things.
Yeah.
Just from looking at stuff.
Yeah, just for visual input.
What makes Dreamer so different?
Well, it's a really good example of how RL is moving beyond simple games into more complex scenarios that are more like the real world.
Okay.
Imagine a robot that can navigate a cluttered room, not because you programmed it with specific instructions, but because it just watched.
Just learned by observing.
Yeah, and figured things out on its own.
So it's kind of like a baby learning to walk.
Yeah, like a baby.
By watching how other people do it.
Yeah, that's a good analogy. Dreamer can learn from its own experiences, but it can also learn by watching videos or demonstrations. Which makes it so much more adaptable than, older types of RL agents.
It's incredible. This is starting to make me think about, like a future where AI can learn in ways that we thought only humans could.
Yeah.
And it's exciting, but it's also a little, I don't know.
A little scary.
It's scary.
Yeah, it's a very powerful technology with the potential to, really change things in so many ways.
Transform many aspects of our lives.
Exactly.
But I think that also means we have to be really careful.
We do.
About how we, develop it and use it.
Responsible AI, yeah.
Okay, let's switch gears for a second and talk about some of those other RL concepts you mentioned.
Sure.
You talked about contextual bandits. Can you remind me what those are all about again?
Yeah, so remember the multi-armed bandit problem?
Oh, with the slot machine.
Yeah, you got to figure out which slot machine to play.
To win the most money.
Maximize your rewards. Well, a contextual bandit, it's like that, but it's a little more complex. Each slot machine now comes with some extra information, a context.
So it's not just about picking the right machine. It's about picking the right machine based on
the situation. Yeah,
some specific information.
Exactly.
Okay, I think I'm getting it. So it's kind of like those personalized recommendations we were talking about.
Exactly.
The system learns about you.
Based on your past behavior.
Which is the context.
That's the context, yeah.
And then it recommends things that you might like.
That you're most likely to click on, yeah.
Okay, so that's how Spotify knows what music I want to listen to.
Yeah.
Even though I don't even know what I want to listen to half the time.
That's the magic of contextual bandits.
And it's not just music in movies, right? This is used in...
Oh, no, it's used all over the place.
Like all sorts of things.
Yeah, online advertising, healthcare, finance.
Anywhere where you need to make a decision based on...
Based on some specific information, some context.
Got it, got it. Now, what about belief state MDPs?
Ooh. Belief state MDPs.
Those sound really interesting.
Yeah, so remember how we talked about regular MDPs, where the agent knows everything about the environment?
Okay.
Well, in a belief state MDP, the agent doesn't have perfect information.
Okay.
So it has to maintain what we call a belief state, which is basically its best guess about what's really going on.
So it's like navigating a maze in the dark?
Yes, exactly. That's a great analogy.
You can't see everything.
You have to use your senses, your memory.
And you have to make your best guess about where you are.
Exactly.
And in this case, the agent is constantly updating its beliefs.
Yeah, based on its observations and its actions.
It's like a detective piecing together clues.
It is, it is.
Okay, so I can see how this would be useful.
Oh, yeah.
In real-world situations where there's a lot of,
uncertainty.
Yeah, like the fog of war.
Exactly.
You don't always know everything.
So are there, like, real-world examples of this?
Yeah, where are belief state MDPs actually used?
Oh, yeah, all over the place. Robotics, navigation, financial modeling. A self-driving car navigating on a foggy road.
Oh, yeah, that makes sense.
It might use a belief state MDP.
To figure out where it is.
Yeah, estimate its position, where the other cars are, even though it can't see everything perfectly.
Okay, yeah. Because it can't just stop driving when it gets foggy.
Exactly.
Okay. These examples are super helpful. I'm starting to really see how these different RL techniques are used.
Yeah.
But before we go any further, I want to circle back to that deadly triad we talked about earlier.
The deadly triad of instability.
Yeah. Can we break down those three factors a little bit more? Like, what makes them so deadly?
Sure. So let's start with function approximation. Remember, value functions tell the agent how good or bad something is.
Yeah, like the scorecard.
Exactly. But in a complex environment, it's impossible to store a separate value for every single possible state.
Right. It would be.
It would be an insanely huge table.
Yeah, like way too much data.
So that's where function approximation comes in. We use machine learning models, things like neural networks, to estimate those values.
Okay, so instead of remembering everything, it's learning a pattern.
Exactly. It's like using a map to navigate a vast territory instead of trying to memorize every single landmark.
Okay, but that sounds like it could be a little bit risky, right?
It can be because the model is just an estimate. It's like using a map that's slightly inaccurate. You might end up taking a detour or getting lost.
You might end up in the wrong spot.
So that's one source of instability. Now, the second one is bootstrapping.
Okay, bootstrapping.
And that's a technique where the agent uses its current estimates.
Which might be wrong.
To update its own estimates. It's like using a rough draft of an essay to revise and improve it. The problem is, if the initial estimates are off, bootstrapping can actually make those errors even bigger.
So it's like a game of telephone.
Yeah.
Where the message gets more and more garbled.
Exactly.
Okay, that's scary. And then what's the third one?
The third one is off-policy learning. And this is when the agent is learning from experiences that were generated by a different policy than the one it's currently using.
So it's like trying to learn to play tennis.
Yeah.
By watching someone else play.
Exactly. You might pick up some useful tips, but you're also likely to pick up some bad habits.
Okay, so that's how off-policy learning can cause problems.
Yeah. So we've got function approximation, bootstrapping, and off-policy learning all working together to create this deadly triad.
It's a recipe for disaster.
It can be, but thankfully researchers are smart.
Yeah, they've got to have some tricks up their sleeves.
They do, they do. We've got things like experience replay.
Experience replay.
Target networks, double Q learning.
Okay, can you give us a quick rundown of how those work? Because I'm really curious now.
Sure. So experience replay, it's like keeping a journal of your past experiences.
Like a diary.
Yeah. And then randomly revisiting those during training.
So it's not just learning from the most recent thing.
No, it's mixing it up.
It's getting broader perspective.
Exactly. And then target networks. Remember we talked about neural networks?
Yeah, for function approximation.
Yeah, so target networks are like copies of those networks.
Okay.
But they're updated more slowly, so it's like having a more stable target to learn from.
So it's like having a teacher or a mentor.
Exactly. And then double Q learning.
Double Q learning.
That one uses two separate networks to estimate the value of actions.
So it's like getting a second opinion.
Yeah, exactly.
Okay, so these techniques, they basically help to stabilize the learning process.
Yeah.
And prevent things from going completely off the rails.
Hopefully.
Yeah.
That's good to know.
And they've been really successful in, addressing the challenges of the deadly triad.
Okay, well, that's reassuring. Now, I'm really curious to hear more about those other fascinating concepts we touched on earlier.
Oh, yeah.
Like intrinsic motivation.
Yeah, curiosity.
Yeah.
Giving AI that sense of wonder.
And hierarchical RL.
Breaking down those complex tasks. Let's start with intrinsic motivation. How do you actually give an AI that sense of curiosity?
Well, it all comes down to how you design the reward system, right? You want to encourage the agent to explore and learn for the sake of learning, not just because it's going to get a cookie or something.
Okay, so how do you do that? I mean, how do you reward an AI for being curious?
One way is to reward the agent for reducing its uncertainty about the world.
Okay.
Remember we talked about belief state MDPs, where the agent has to make a guess about what's really going on?
Yeah, like the maze in the dark.
Exactly. So you can reward the agent for making observations that reduce the uncertainty in its belief state.
So it's like rewarding a scientist for conducting an experiment that yields new data.
Yeah, or an explorer for mapping out uncharted territory.
The more you know, the better.
Yeah, the more confident you become in your understanding of how things work.
Makes sense.
Yeah.
The paper also mentioned rewarding the agent for exploring new states or taking new actions, things it hasn't done before.
Novelty, yeah.
How does that work?
Imagine you're playing a video game, and you could just stick to the main path and try to beat it as fast as possible.
Yeah, just get to the end.
But what if you wander off the beaten path, you explore those hidden areas, you find those secrets? That's what we want to encourage.
So it's like giving a bonus to a traveler who goes off the tourist track and discovers a hidden gem.
Exactly. We want to encourage that sense of adventure, that willingness to try new things.
I love that. It's like we're giving these AI agents a sense of wonder, like a thirst for knowledge.
It's a fascinating area of research.
It is. Okay, let's talk about hierarchical RL. You mentioned this as a way to tackle more complex problems.
Yeah, it's all about breaking down those big problems into smaller, more manageable chunks. Sort of like organizing a big project into smaller milestones.
Divide and conquer.
Exactly. Or writing a book chapter by chapter.
So instead of trying to solve the entire problem at once,
yeah, it's overwhelming.
You break it down into these smaller sub-goals.
And each sub-goal leads you closer to that final solution.
Okay, so it's like teaching a robot to cook a meal.
Yeah.
Instead of trying to program all the steps at once, you teach it to chop vegetables first.
Then boil the water, stir the ingredients.
One step at a time.
Exactly. And that makes it much easier for the agent to learn these complex behaviors.
Like a recipe book.
Yeah, a step-by-step guide.
Are there any real-world applications of this?
Oh, yeah, tons. Robotics, game playing, natural language processing. Think about a robot learning to navigate a complex environment.
Okay.
It could use hierarchical RL to break down the task into smaller subtasks.
Go to the door, open the door, enter the room.
Exactly. Much easier to learn that way.
Okay, that's super cool. Now, what about offline RL? You mentioned it as a way to learn from existing data without actually having to interact with the environment.
Yeah, it's like learning from the past, right?
Why is that so important?
Well, in a lot of real-world situations, it's just not practical or safe to let an AI agent learn by trial and error.
Right. There are consequences.
Think about healthcare. You wouldn't want an AI system experimenting with different treatments on real patients.
No, absolutely not.
Not without a very good understanding of the risks.
So offline RL lets us train these AI systems using data from past experiences, but without putting people or systems at risk.
Exactly. You're learning from the mistakes and successes of others.
I get it. But that sounds incredibly difficult. How do you train an AI agent effectively when it can't actually, interact with the world?
It is a challenge, but there are techniques. One approach is called importance sampling.
Importance sampling?
Where you basically weight the data points in your data set based on how relevant they are to the policy you're trying to learn.
So it's like you're not treating all the data equally.
No, some data points are more valuable than others.
You're focusing on the ones that are most relevant to the task at hand.
Exactly. And another approach is to use uncertainty estimates.
Uncertainty estimates.
Where you penalize the agent for taking actions that lead to states where it's not very confident in its knowledge.
So it's like, stick to what you know.
Yeah, don't wander off into the unknown too much. It could be dangerous.
Okay, that makes sense. Wow, we have covered so much ground today. I feel like I've learned a ton about reinforcement learning.
It's a huge field, but hopefully this has given you a good overview.
It really has. I mean, we talked about the basics, we explored some of those real-world examples, and we even touched on some of the challenges and future directions of the field.
And it's just getting started. There's so much more to discover.
I know, it's incredibly exciting. So to our listeners, I hope you've enjoyed this deep dive into reinforcement learning as much as we have.
Yeah, thanks for joining us.
And until next time, keep learning, keep exploring, and who knows, maybe you'll be the one making the next big breakthrough in AI.
The future is full of possibilities.
It really is.